I'm sharing my screen. Yes. Think my screen is visible. Okay. So today I will explain you about this uh, asynchronous active low reset 3-bit synchronous counter. Okay. First I will with the programming also I will explain. Okay. So what is this asynchronous active low reset and all this. Okay. So first I will design a one second. One second. Yeah. Okay. So first I will design uh, so 3-bit first I will design 3-bit up counter. Okay, 3-bit up counter. Okay, how to design this 3-bit up counter? There are steps are there. First step 1. Okay, step 1. What is step 1? Choose the type of flip flop. Okay, I am choose let us choose T flip flop. Okay, I am choosing T flip flop. Okay, choose T flip flop. And step 2. Step 2. So what is step 2? Draw that state transition diagram. Draw the state transition diagram. Okay, transition diagram. So you need to draw the state transition diagram. And next step 3, fill the excitation values. Fill the excitation values. Excitation values. Okay, excitation values for corresponding flip flop. Corresponding flip flop. Okay, so these are the steps. So here I am drawing the excitation values. Okay, I am drawing the excitation values and corresponding flip flop. So I am drawing the table. So what is this? Present state, and next state, okay, next state, and input. Okay, I'll tell you the Verilog code also. I will execute this code in QuestaSim. Okay, I will explain the code also, and I will execute this code using QuestaSim. So Q2, Q1, and Q0. Okay, this is what Q2 plus, Q1 plus, and Q0 plus. Okay, and inputs you take as what? T2, T1, and T0. Okay, so here 3 inputs are there. How many possible combinations? 8 possible combinations. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so that means here you need to draw the state diagram. So this is mod 8 counter. Mod 8 counter 3-bit up counter. So if it is present state is 0, if 1 clock is applied, it will go to the next state 1, and 1 clock is applied, it will go to the second stage 2. Okay, next third stage 3, and fourth stage 4. Okay, and next one more clock pulse 5th, next 6. Okay, and next 7. Okay, after that it will come to the initial state. So if present state is what? Present state is 0 0 0. What is the next state? 0 0 1. If present state is 0 0 1, what is the next state? 0 1 0. If present state is 0 1 0, what is the next state? 0 1 1. If present state is 0 1 1, what is the next state? 1 0 0. If present state is 1 0 0, what is the next state? 1 0 1. If present state is 1 0 1, what is the next state? 6 1 1 0. If present state is 1 1 0, what is the next state? 1 1 1. If present state is 1 1 1, it will come to the initial state. Okay, and you need to draw the inputs. Okay, so you know the excitation table for T flip flop. What is the excitation table? Present state and next state and T flip flop. Okay, with inputs. Okay, so 0 0 0 1 1 0 and 1 1. Okay, so 0 1 1 0. Okay, this is like XOR gate only. Okay, so XOR gate means you need to see these two. Okay, so here so T2 I am writing, so both are 0 0 0 only. Okay, this is 0, this is 0. Okay, and next 0 1 1. Okay, and next this is 0, this is 0, this is 0, and this is 1. Okay, and next 0 0 0 0 1 1 1 1 0 and 1 0 1, and next this is what this is 0, okay, 0 1 1 and 1 1 0 and 1 0 1, okay, and every time this will be 1 only, okay, this will be 1 only, this will be 1 only. Why? Because all are 1 only, okay. So from here I can write so I can draw the K map for both T2 T1 and T 0. So you need to draw the K map. So from here I can say that T 0 equal to what? 1 only, T 0 equal to 1, okay. So K map for T1, so T1 equal to what are the inputs? T1 of Q1 Q0, so T1 of Q2 Q1 Q0, okay. Q2 Q1 Q0 equal to what? Summation of M of what are the min terms you need to write? So this is 0 1 2 3 4 5 6 and 7, okay. So whatever the ones are there you need to write. So this is 1 3 1357, no? 1357, okay. Just you draw the K map for this T1, okay. T1 3 variable K map. So here what you will get, so this is 1 second, yeah. So here if you see this is inputs is Q2 Q1 Q0 0 1 0 0 0 1 1 0 1 1 0 1 2 3, next 4 5 6 7, okay. So 1 3 5 7, okay, 1 3 5 7. So this if you, this is a quad, so this is equal to what? T1 equal to Q0, T1 equal to Q0, okay. And T2 equal to what? Summation of M of what are the min terms? 3 and 7, 3 and 7, okay. So you need to draw the K map, okay. So this is Q2 Q1 Q0 0 1 0 0 0 1 1 0 1 1, okay. 0 1 0 1 2 3, okay. Next 4 5 6 7. So here 3 and 7 means what? This is T2 equal to what? T2 equal to Q1 Q0, okay. Q1 Q0, okay. So you got the expressions, okay. So you got the expressions. So what are the expressions you got? So here T1 equal to, so I am writing separately. So here T0 equal to what? 1, okay. And next T1 equal to Q0 and T2 equal to what? Q1 Q0, okay. Q1 Q0, okay. I am writing this, okay. So next what is the next thing you need to design, no? So you need to design the synchronous up counter, okay. So how many flip-flops are required? So basically counters are designed by using what? So counters are designed by using JK flip-flop and T flip-flop, which will be operated in which mode? Toggle mode, that you know, okay. So when J equal to 1, K equal to 1, then Qn plus 1 equal to what? Qn bar, okay. And when T equal to 1 also, Qn plus 1 equal to what? Qn bar, okay. So that is toggle mode. So basically how many flip-flops are required? 3 flip-flops are required. For n-bit counter you need n flip-flops. For 3-bit counter you need 3 flip-flops, okay. So what is the type of flip-flop I am using? T flip-flop I am using, okay. So T flip-flop I am using, okay. So this is let us take yes. So this is T0 Q0 T1 Q1 T2 Q2, okay. So here T0 equal to what? T0 is always connected with 1, okay. Q0 equal to T0, T1 equal to what? Q0, T1 equal to Q1, and T2 equal to, I can connect with an AND gate. This is one AND gate. This output is given to T2. Q1 Q0. So from Q1 one input is coming, and Q0 is also one input is coming. Okay, this is what Q1 Q0. Okay, and common clock is given. Okay, common clock is given. Let us take this is negage of, okay, clock, or you can give passage also. In program I am using passage of clock, so that's why I am giving passage of clock. So when it is going from, clock is going from 0 to 1 only, this will be activated. That's why this is the output will change. This is nothing but passage of clock. Okay, this is nothing but passage of clock. Okay, so here I'm designing this. Okay, so mm so here this is passage of clock, and coming to the reset, you need to use asynchronous reset. So asynchronous reset means this is these all given to these all are given to reset underscore n. Okay, this is a predefined word in Verilog. So this is given to which one means asynchronous input, that is clear. Asynchronous input clear. Okay, so that means what happens, this is active low reset. When it is active low reset, we need to give it to the bubble. Okay, so when reset underscore n, that is equal to 0, so the output of all flops, okay, all flops will be what, all flops will be 0 only. Okay, so that means so it will start from that is q2, q1 and q0. Okay, so always for the counter, rightmost bit is MSB bit and leftmost bit is LSB bit. Leftmost counter is LSB of the counter. So here always this clock is connected to this LSB of the flip flop. LSB of the flip flop always toggle. Okay, it will always toggle. Okay, so here this will start from initial state. Okay, this is nothing but which mode? Reset mode. This is nothing but reset mode. When reset underscore n equal to 1, so that means clear. So that means this reset is inactive. So this is active. Reset will be activated, and this is deactivated. Reset state is deactivated. So when reset is deactivated, so it will count q2, q1 and q0. It will start from where initial state 0 0 0 to the final state 1 1 1. After that it will come to the initial state. Okay, so this is nothing but what, functional mode. This is nothing but functional mode. Okay, so I will show you the program and I will execute this one with the Questasim. Okay, I hope you understood this operation. Okay, I'm executing this. Okay, 1 second. Yes. Okay, yeah. So just I'm showing this. I think my screen is visible. Okay, so I'm opening this. RTL codes, counter, synchronous counter, RTL design, and I am using synchronous counter increment by 1. Okay, counter increment by 1. Okay, so if you see this program, I am wrote in GVim. Okay, I wrote in GVim. I already told, no, GVim is a powerful editor. So we need to use some commands so that we can use this GVim. Okay, so module counter increment by 1. So whatever the inputs are there, that I need to initialize with the wire input wire clock reset wire reset underscore n. So this is I am using asynchronous active low reset. That's why input wire reset n. Okay, output range how many bits? 3 bits. So 3 bits means output range 2:0 counter. Okay, 2:0 counter, and I will use one more intermediate variable, that is count. Okay, so that this one I am using in the behavioral modeling, that is always block. So while I am using this always block, that's why I need to initialize this data type as reg 2 down to 0 count. Okay, this is 3 bit. Okay, and always at the rate passage of clock or negate of reset. Okay, this is sensitivity list. Okay, so sensitivity list in the last class I told you, like reset removal is synchronous with the clock, but reset applied, okay, reset applied is asynchronous with the clock. Okay, so that's why we are using the sensitivity list, that is passage of clock and negate of reset begin if not of reset. So if reset equal to 0, so count becomes what? Count will be initialized to 0. Okay, all are 0. Okay, 3 tick binary 0 0 0. Else count is I am using non-blocking operator. Okay, between in this always block I need to use non-blocking operator. So count is so initialize less than or equal to count plus 1 tick binary 1. Okay, and after that whatever the counter is there, so counter is I need to use a continuous assignment statement, assign counter equal to what? Count end and end module. Okay, this is the program. Hope you understood. Next, for the test bench, okay, I am opening the test bench. I told you know you need to create 3 files like RTL, sim and TB. Okay, simulation, not simulation, TB. Okay, TB counter counter increment by 1. Okay, TB counter increment by 1. Okay, so this is I am opening this select font 16. Okay, see here module TB counter increment, and this is counter increment by 2. 1 second, counter increment by 1, counter increment by 1, where a TB parameter counter increment by 1. Parameter, this is parameter. Okay, counter increment by, okay, this name should be same. Okay, I didn't change the name. So this module name and my file name should be same. If I press IE, it will be in editor mode. Okay, counter increment by 1. Okay, so here this one what I am doing, module TB counter increment by 1. Okay, counter increment by 1. So whatever the out inputs are there, that I need to initialize with reg. Okay, why? Because these reg variables I am using in the procedural block, that is initial and begin. Okay, initial and this initial begin block. Okay, this x and y, that's why I need to use this as reg, and y is what, y is 2 down to 0 z. Okay, and next I need to instantiate the design. So counter increment by this design is 1 second, okay, it will be editor mode only. Increment by 1, counter increment by 1, dot of clock, I need to use what, instantiation by name. Okay, this is nothing but what, instantiation by name. So connection means connection by name. So whatever the design variables are there, those are we need to represent outside the bracket. Okay, whatever the test bench variables are there, that you need to initialize in inside the bracket. Okay, so this is counter increment by 1, and UIT is nothing but instance name, that is unit under test. Clock generation, so you are generating the clock for 10 nanoseconds. Initial x equal to 0, always #5 x equal to not of x. And stimulus means you need to assert the reset, that means you need to make y equal to 0. After 7 time units, what you are making, you are deasserting the reset for after 7 nanoseconds. After that, you are running for this code for how many time units, 100 time units you are working. Okay, this is the test bench. I need to verify the functionality of this circuit. Okay, so this one I will save. Okay, next, so here counter divide, counter increment by 1. Okay, what is this file? I will see. This one, I think this file is not required. Okay, I can delete. This one is by using parameter. Okay, like this files will create, we can delete this, not required. This one not required, this one not required. Okay, so this is about the test bench and code. Okay, next what I need to do, I need to open this QuestaSim. Okay, I need to open this QuestaSim. So QuestaSim, so 1 second, something happened. License. Okay, this I will open. Yeah, this I can open. It's asking for license. Okay. Okay, I will see. I will show in Xilinx Vivado. Okay, there is a license issue. Okay, I need to verify. Check this. Okay. Okay. 1 second. I am opening this one. Xilinx Vivado. I'll show in Xilinx Vivado. Okay. Synchronous counter. Synchronous counter. Synchronous counter. Already wrote the program in Xilinx Vivado. Just I am opening and I am showing this. This is counter increment by 1. Okay, same thing, same program, whatever I explained, this is counter increment by 1. Okay, and simulation here 6 simulation sources are there. So here which one, counter increment by 1. Okay, so whatever you are simulating, that should be you need to right click and set as top module. Okay, anyway it is there in top module. Suppose you want to simulate this. Okay, you want to simulate this, so here you need to set as top, you need to make set as top. Okay, So that will make as set as stop. Okay, TB parameter will be set as stop. Okay, counter increment by 1. Okay, counter increment by 1 set as stop. Okay, and design also, if you want to see the design also, so that you need to make as 1. Okay, and next elaborate the design. Suppose I want to see the design, how the counter will be there. I want to see the design, just to elaborate the design. And here one of the advantages, you will get the design. Okay, you will get the design. See here, so that means here D flip-flops are there. Okay, D flip-flops are there, and this is asynchronous reset. You are giving through the bubble, that is asynchronous reset. And how many D flip-flops? 4 D flip-flops are there, and this will be feedback to the adder circuit. One adder circuit is there. Okay, adder is incremented by what? 1. Okay, adder is incremented by 1, and it is given to D flip-flop. Okay, this is my schematic. Okay, this is my schematic, and you can see in the this also. Okay, this is adder circuit. Okay, like this you can see. Okay, floor planning and all those things you can see. Okay, counter 0. Okay, counter 1. Okay, all these things we can see. And first I want to run the simulation, run the behavioral simulation. So here I will get the simulation. So just expand this and fit to page. You see here. So that means x is what? X is clock. Okay. Y is nothing but reset. Okay. So during when, so here this is nothing but what? Reset mode. When it is reset mode, counter will be what? In initial state only. So when reset is moving from where to where, when reset is moving from reset mode to functional mode, immediately counter is not responding. When it is responding, during the passage only it is responding. Okay, so that means I told you, no, like reset removal is synchronous. Okay, synchronous with the clock. Okay, reset removal is what? The operation is synchronous with the clock. Here itself it will not change. Okay, so during the synchronous clock edge, the output is changing. See here, output is changing. Output is changing here also. During the passage of clock, it is counting from where to where? 0 to 7. After 7, what happens? It will come to the initial state. Again it will start counting. Okay, it will start counting. So like this you can see the, so this values also will get. Okay, so at 111, so here what you got, if you want to see, you will get 111. Okay, here you will get 101. Here you will get 100. 4 means 100. So like this you can see the behavioral modeling also. Okay, behavioral modeling also. Yes. Parameter also I told, I wrote parameter means same, like suppose client will ask, I want a 4-bit counter, 8-bit counter. Okay, there I can't change the design, I can use parameter. Okay, this is parameter program. Okay, so parameter program means like here what I given, I need to use one module parameter counter incremented by 1. So I need to initialize parameter width 3 and parameter step 1. Okay, I can change these values also. Width, if I want 8-bit counter, I can change 8. Okay, step into 8 into 3. Okay, step like step 1 means counter divide. If I want to divide increment by 2 means what, I can give step to 1. Okay, input wire clock, input reset of n, output width minus 1 is to 0 counter. So width minus 1, that means what? 3. 3 means what? 3 minus 1. 2 down to 0, no? 3 bits. Okay. If a width equal to 4, 4 minus 1, 3 minus 3 is to 0. So this is 4 bits. So reg width minus 1 is to 0, that is count. Always at the rate passage of clock, negate of reset, begin, not of reset, count equal to what? Width 1 tick binary 0. You are initializing the count. Okay, when reset is activated. When it is else, count equal to count plus step, and assign counter equal to count. Okay, this is the program. And test bench also same. Test bench, if you see this one, yeah, this one. Okay, I'm selecting the font size. I'm initializing this TB parameter counter incremented by, here you need to write This is incremented by 1, no? Incremented by 1 means what? This is 1, okay? Parameters, a equal to 3, parameter b equal to 1, and whatever the inputs are there, that initialized to reg variable, whatever the outputs are there, that initialized to wire. So a minus 1 means what? 2 down to 0. So I need to instantiate. First you need to instantiate the parameter, okay? So parameter incremented by 1 ash dot width dot step, these are nothing but design parameters. A and B are nothing but test bench parameters, okay? And UUT, unit and test, clock, reset of n, counter are design inputs, and these are nothing but test bench inputs, okay? And I need to generate the clock. So how to generate the clock initial, I need to initialize the clock, and hash by clock equal to not of clock, and I need to assert the clock, and after 7 time units I need to deassert the clock, and I need to run for 100 time units, okay? So this is the test bench, okay? This is the test bench, okay? So I can run in Xilinx Vivado. Just closing this elaborate design, here what I can do, TB parameter, incremented by 2 I wrote, just select as stop, just incremented by 2 you'll get, okay? I need to select as stop, run simulation, run behavioral simulation. So incremented by 1 means what? It will increment by 1. Incremented by 2 means it will be incremented by 2. You'll get 2, 4 like that. 4-bit counter you need to use, okay? So here you see. So this is my simulation, okay? So during what happens, I need to see this counter, no? So when reset equal to 1, what happens, it is going from reset mode to functional mode. Immediately the output, counter output will not change, it will be in the initial state only. When it will change, during the passage of clock it will change, okay? So 0, 2, next 4, next 6, 8, A, okay? And after A, 10, 11, and 10, 12, 12 means C, and 12, 14, 14 means E. Again it will start from the initial state, okay? So this is about counter using parameter. Counter using parameter increment by 1 also you can write, okay? So this is about this section, okay? This session.